Hi everyone, my name is Alex. I'm one of the organizers of CaquiCoders community. Thank you for your participations. We started to have events in English apart from the normal meetups we have to motivate the developers in Brazil to learn English, and feel free to ask questions in the chat box. And if you have any issue with audio from someone, please say in the comments as well. So we'll start to this event with the presentation from Mauro. He is going to talk from Italy, and after that, Ivan, can you introduce yourself, Mauro, please?
Sure. Thanks for having me and welcome everyone. So my name is, as Alexander just said, Mauro Servienti, and I'm Italian and I live in Italy, nearby Milan. And I work as a solution architect in particular software. And we make a tool called N-Service Bus that is basically a sort of a messaging framework for distributed systems.
Thank you very much. Can you introduce yourself, Ivan, please?
Hi, everybody. My name is Yvan Polevich. I work for Nordex Bank here in Stockholm, and I'm going to talk about clean architecture later today. You may know me by GitHub repositories, and my most popular is the clean architecture manga. So if you have found it by some mistake that you open that page, then I am one of the supporters, and that's it.
Thank you very much, Ivan. I'm going to share your screen, Mauro. Have a good talk.
Thank you very much. So welcome again, and welcome to designing a UI for microservices. As said, my name is Mauro Servienti. So I'm a remote worker. So I'm fully working remotely for an international company. Well, by the way, we are all remote workers. So the interesting thing of the company I work for is that there's no one living and working in the same city as anyone else in the world. So we are all remote. In fact, we call each other a kind of dispersed company instead of distributed one. And the problem I have is that the flat where we live in with my family is too small. So it's even too small for 3 people. So it's basically impossible to find a place for myself to work with. So what I did is that I decided to rent a small office that is roughly 1 kilometer apart. And what I do is basically I bike ride there every single time I have to work. And right now I am in my office. So one of the problems is that I also like bananas to have as a snack. And if you ever had an experience of bike riding while carrying a banana with you, the interesting problem is that your banana is not really happy at the end of the bike ride. So it happens that the backpack basically eats your banana. So, and that's the thing that once you experience it a couple of times, you really want to fix. So what I did is that I headed to my favorite online store and decided to buy something to solve the problem to begin with. And I found this, a banana protector. By the way, there's tons of them. So there's a list of possible choices that is kind of endless. And as soon as I was looking at this page, and the first thing that came to my mind as the kind of solution architect that always lives in the back of my mind, started asking, but hold on a second, does a page like that really exist? I mean, think about, let's try to imagine the Amazon code base, like if it was an MVC.NET application. Does a product controller class exist in the code base? Does a product details view exist in the code base? And that's an interesting question, because if we have a deeper look at what the kind of banana protector details page is, we can start saying that a page like that doesn't really exist. We have a bunch of information living in the page that are probably coming from different sources. So if we try to identify them, we can immediately say, well, hold on. There's probably things coming from something we can call a catalog, like, for example, the product name or the product images, or even the customer reviews and the product stars, right? And then we have the price. That's probably coming from something we can call sales. There's someone else that is different from the catalog, making decisions about the price we want to sell the item for. And then there's a warehouse that has information about how many items are left in stock. And then finally, there's something like shipping, for example, that tells to the user, in this case me, well, this item is eligible for free shipping. So there isn't really a single place where all these information are stored in order to be retrieved and then displayed on the page. And by the way, warehouse is usually a liar. So there isn't really 9 items left in stock. That's by psychology to try to convince you to buy the item, but that's another story. So what are we watching here? We're basically observing something we can call domain model decomposition. So what we have is really the single responsibility principle applied to data. So we have services or microservices, if you will, or aggregates, bounded context, subdomains, call them as you will. Doesn't really matter the name you give them. I like to call them services, but that's my preference. So we have services owning their own piece of information. Each one owns a subset of the information that is then displayed to the user on what the user perceives like a single page, right? And at this point, if that's true, the next question should be, how can we design something like that? So think about it. We have information coming in, stored in different places that needs to be aggregated in some way onto a single page to display users something, because we cannot expect users to navigate from page to page, saying on page 1, hey, here is a banana protect for you. Go to the next page to see the price, and then go to the next page to see if it's available, and then go to the next page to see how much how does it cost to ship it, or if it's free, whatever. And the first reaction to such a question, how can we design something like that, is a temptation. So it's very tempting to come up with a technical solution to what's a non-technical problem. So we have these 4 services, each one owning a piece of the information. And it's very easy to say, well, what about we do something very easy? We extract data from these services into what you can call a denormalized API storage. Think to it like Elasticsearch, whatever, a relational database. That doesn't really matter. So we group data related to each other into what we call a product, into a denormalized storage that is then consumed by a client. And we call what's exchanged between the denormalized storage and the client a view model. Someone called them read models. So the sad truth, if you think about it, is that that's cache. So we're basically extracting information from what they are stored and owned, that's the most important thing, into something that doesn't own anything. And then we'll start having all the problems that all the caches have. So what happens if the price change? Now we need to update the cache. What happens if the items stored in the warehouse, so the stock availability changes? We have to update the cache. What happens if the description, that is probably unlikely to change that quickly, changes, we have to update the cache. And what happens if we stored into the cache that thing as a single document? So let's imagine that we grab data from multiple places. We composed a nice looking JSON document and we store that into the cache, because obviously we want something that is schemaless, probably. So we have a single document. Now someone comes along and says, well, you know what? The price changed. And what do we have to do? Drop the document and create it again. So basically now we are doing, putting stress onto services just because one of them decided to change one of the information contained into the document, right? And by the way, we have a problem that not everything can be cached. So I intentionally took the screenshot from the US website, where most of the things cannot be shipped where I live. So this item, if bought in the US, it's not really $10 and free shipping. Well, it's $10 and free shipping if you live in the US. But if you live outside the US, it cannot be shipped. And that kind of information cannot be cached at all. Well, it can be cached, if you think about it. You can cache the entire possible combinations of users and locations and products and cache all of them. And then immediately tell whatever meaning of immediately we want to use now, that that kind of stuff cannot be shipped to Italy if Mauro is logged in. But it's not feasible at all, right? So what we want to do now is step back a little for a second and go back to a sort of drawing board and try to understand what's the problem we're trying to solve. And the problem we're trying to solve is not a caching problem, it's a reporting problem. Yeah, I know, sounds weird, right? So the thing is that displaying data, regardless of the fact that it's an HTML page or paper, it's always a reporting and integration issue. We're crossing a boundary. So data flow out of each service to the user. Data stored in catalog are flowing out, going to the user machine. The price is going to the user machine, and so on. So given that the users are already pulling things on demand, why shouldn't we benefit of that? So what's the difference between building a PDF on the fly to send it to users via email, or building an HTML page on the fly and sending that to a browser via HTTP? It's the same problem, basically. So we can start thinking about it as a thing that we call view model composition. Let's start from the user now. So the user wants to, well, where the user can be anything. A machine, a browser on a user machine, wants to display something that is identified by a URL, where a URL is a URI that is a unique key in the end. So we have something that is /products/1, and that's on the client, whatever client means in this scenario. And we have something that we can identify as a sort of primary key. And then we have these 4 services, each one containing a piece of the information that we want to retrieve. If they were to share the same primary key, so everyone store their own piece of information using 1 as the primary key for the part of the information related to the product 1, then what we can do is basically pull that information out of each service on the fly and compose the view model on the client itself. And there's an important thing here to take into account. Client doesn't really mean the user device. So client is whatever composes the information that is then sent to the user device. So it can be the browser on the user device, but it can be something sitting in the middle, like a reverse proxy, or it can be the web server. So at any stage, everything can be seen as a client. right? So if we want to dive a little bit deeper into this, we can see these 4 services laid out on the right, and then we have an incoming HTTP request to try to get information related to /product/1. And this kind of information goes to something that we can start calling a composition gateway. That composition gateway is the logical thing that composes information. As we said, it can live on the client side. So in the browser, it can live sitting in the middle, like on a reverse proxy, or it can be on the web server, the final web server. So the first thing that the composition gateway does is creates an empty view model. Something that will be returned in some way to the requestor. And then it does a thing called request matching. That is basically asking to services, is there any one of you interested in this URL, /product/1? And in our sample, all of them will say yes. Yes, we are all interested in this request. And then find the third step is the composition step. So what happens at the composition step is that each one of them go back to their own backend or to their own storage, retrieve the information they need to retrieve based on the incoming URL, so the /product/1, get it back into the composition gateway and fills the view model that was created empty by the composition gateway. And finally, the composed view model is returned to the client. We can dive deeper even more and try to look at it from the coding perspective. So code samples will be in .NET, but it can be applied to any language, basically. They're very, very simple. So let's imagine that we have someone that is trying to display a product like the banana protector. One of these handler that has displayed on this image can be the product details handler from the catalog, for example. And can be a class like this one. So product details get handler that implements an interface called iCompositionRequests handler. The first thing that, so the iComposition request handler forces you to implement a method called handle that receives an HTTP request and returns a task because it's asynchronous. So we said that the first thing that we need to do is something called request matching. So who is interested in handling a specific request? And we're using the same syntax that MVC used us to use, that is attributes. So we can decorate this class, well, this method specifically, with an HTTP GET with a template saying, hey, if there's an incoming request that matches this template, I'm interested in handling it. And that's the case. So the incoming request is /product/1, so that matches this HTTP GET attribute template. So that means that our handle method is then invoked when the composition process starts. And when the composition process starts, the first thing that we do is we retrieve from the HTTP context the values that we are interested in this specific case, just the ID. And then we go back to our backend. In this case, it's warehouse, saying, hey, warehouse backend, can you please give me back what's the inventory status of the product identified by the ID 1? And for simplicity, we're using dynamic objects here, just for the sake of the demo. And then we retrieve from the request, the composed request model that was originally created empty by the composition gateway. And we fill in our own information. So we append to that dynamic VM, like if it was a dictionary. Think of, if you're familiar with JavaScript, think to it like a JSON object, really. So it comes in empty, and everyone can fill in data from, they retrieve from their own source. And basically what happens is that now this handler coming from warehouse is composing data into that dynamic VM. And you can imagine that the same happens for sales, the same happens for catalog, the same happens for shipping. At the end of the process, well, these handlers are invoked in parallel. When all of them are done, what happens is that the dynamic view model that was created empty is filled with data that can be returned to the caller or to the UI, if that's the case. The important bit here is that each handler can retrieve data from wherever they want. So in the sample, I'm using HTTP to retrieve data again, but that's not really required. So given that the handler is logically owned by the same service that owns the data, there's nothing wrong inside the handler code to reach out directly to the service database, because they belong to the same logical service. There's no need to keep them decoupled. They change together because they belong to the same service. And once the composition process is complete, basically the output looks like this. So we have a JSON that contains a product name, the banana holder, the product description, out travel include banana protector storage box. We have a product price, shipping options, the current inventory, and if it's out of stock or not. And you can see the ownership here. So each box represents data filled in by different services. At this point, the question is all what glitters gold? So are we done, essentially? Is that enough? And the answer is, unfortunately, no. Because we have a problem. Grids. It's always nice to have fun problem to deal with. So what's the problem with grids or lists? Is that each item in the list is composed, right? So if each item in the list is composed, you can immediately spot the problem. Think about it. It's basically a sort of select n+1 over HTTP. Because if we apply the same logic we just applied to this list, that we applied to a single item to this list, what happens is that when we need to compose the first item, 4 HTTP requests or 4 database calls will go out for the first product, and then 4 more for the second product, and then 4 more for the third product. So basically, we end up with a number of requests that is the number of services times the number of products we're trying to display. And if that's 1, that's acceptable. If they are 20, that's not acceptable anymore, especially because if you think that to a real production system, there will be probably more services involved, and you don't want to end up with a sort of flood of HTTP requests that are going to kill all the backends just because you're displaying a list. So let's try to see how to handle grids in this case. Let's imagine something like a homepage where we're trying to display a list of available products. And I'm using this this scenario because it's exactly the one that's contained in the demo that I'm going to share with you at the end of the talk. So we're trying to hit a route that is /available/products. That should give us back the list of available products in the store. And we want to give back to the UI a view model that is basically an array of products composed with information coming from different services. Now, who owns that? That's the first question we should be able to answer. Catalog is the one that makes decision if a product is available or not. And what catalog does when this request comes in is that it loads the list of available products, where the list of available products is essentially a list of IDs or primary keys, whatever kind of primary key you're using in your system. So catalog gets back a list of primary keys, and what it does is that it publishes an event saying, hey, I loaded available products. Is there anyone interested in available products? And in this case, there's sales and someone else, let's imagine warehouse, saying yes. And by saying yes, it's because they register themselves to the available products loaded event. So what they're doing is that they are receiving the event, they are going back to their own backends, they are retrieving data based on the product keys published in the events, and finally, each one of them is composing data into the view model. So what happens is that if you look at it from the coding perspective, we have an API that looks familiar because it's essentially the same as before. So we have an available products get handler saying, hey, I am a composition request handler, and my implementation looks like this. I removed the attribute for clarity, mostly for space on slides. And what happens is that the first thing that they do is, that's the one coming from catalog. So from the product catalog, the first thing that I'm doing is I'm going to the product catalog backend, asking for the list of available products. What comes back in this case is a list of integers. So it's the list of primary keys that should be displayed on the home page. That's converted into a dictionary where the dictionary key is the primary key and the dictionary value is the empty view model. So in that dictionary, after that conversion, there will be as many items as many available products, where all the keys, all the primary keys are used as dictionary keys, and for each one of the key, there will be an empty view model created, available and ready to be filled. And then I'm raising an event. So I'm saying, hey, view model, can you please raise an event saying available products loaded? And that's it. What a subscriber looks like. I'm an available products subscriber. And what I'm doing is saying, hey, whenever there's an incoming request, I like to subscribe to the available products loaded event. And even in this case, I removed from the slides the HTTP get attribute template so that I can filter out subscribers based on the incoming URL. And whenever the event is fired, the subscriber receives the event that contains that property, available products view model, that is the dictionary created by the other one. It's retrieving all the keys. It's going to its own backend. And once it's retrieved all the product prices in this case, so this one is coming from sales, it's for reaching over them and filling in the product price for each one of the view model. And the same happens for warehouse, shipping, and all the other services interested in participating into composing the homepage. And finally, we go back to the composition process because we awaited the previous event. So when the raise event completes, all the subscribers have received the event, they've done their job, and they've filled in the available products. And finally, we're pushing to the view model the available products, extracting that from the list of values into the dictionary. So as you can see, the handler that's coming from catalog knows nothing about what's going on into the products. The output is very similar to what we had before. So it's a JSON object containing a list of available products where each item in the list is basically composed by data coming from different services. In this case, 3 out of 4. So shipping is not participating in this composition process for the homepage. One important bit is that the composition process actors, so in this case, the catalog handler, the sales handler, the shipping handler, and the warehouse handler, they belong to the same service as their own services. So the catalog handler belongs to catalog, and the sales handler belongs to sales, the shipping handler belongs to shipping, and the warehouse handler belongs to warehouse, regardless of where they are deployed. So if they are deployed into the web server, they belong to their own services. Even if they are deployed into the composition gateway or as JavaScript component into the browser, they still belong to their own service, to their own logical service. This means that during the request matching and composition process, they are allowed to access their own data. That's why I said before, you don't really need to use HTTP to do this. The demo uses HTTP, but each handler can access, they can directly talk to their own backend, and they can even directly talk to their own database because they're basically in the same logical service. What do we have now? So if we have each piece of information that is owned by each service, and this piece of information can be composed on the fly and then shipped once composed to the UI, what we have is a thing that we can call vertical ownership. So if we still using our own 4 services, we can expand them and say, you know what? If you look at them and look inside, we have catalog that can be, for example, something like a document database that has HTTP support, and then we just have a web proxy in front of it. And then we can have sales, that is a regular database with a backend, because we have a lot of processing and a lot of business logic into sales, and an API in front of it. And then we have shipping, and we do nothing for shipping. So it's just a REST interface to a third-party API. And then we have a warehouse that is very similar to sales, where we have a backend, an API, and a database. And in front of it, we have a user interface. We haven't talked about the user interface yet. We just talked about data so far. The interesting thing is that we can finally cache stuff. So if we have full vertical ownership over data, now each service can define a cache policy for its own data. So catalog, for example, can say, I'm going to cache description and names and images for a month. Who cares? Even forever, right? So if something goes badly and there's a typo and someone didn't catch that while previewing the product, we're going to manually wipe that item from the cache and rebuild the cache. And sales can cache stuff for 10 minutes, because that's the most important things. We don't want to allow users to buy stuff where the price changed too easily. And shipping, we don't own it, so we're caching nothing. The third party might cache stuff. And then we have warehouse, where we said before, warehouse always lies. So they have a 24 hours cache. They're telling us there are 9 items in stock, but the last update of that information was 20 hours ago. So we might end up buying something that doesn't exist. But that's not a technical problem we are here to solve. That's a business problem, right? So the composition gateway sits in front of all of this. And each service deploys into the composition gateway their own handler. And as we said before, handlers belong to the service, so they are part of that vertical slice. What's remaining here? Because the title of the talk was Designing a UI for Microservices. Yes, the user interface is the elephant in the room, right? And my main goal tonight is to, well, tonight, for me it's night, but my main goal today is to convince you that the user interface is the last of your problems. If we have the ability to compose data on the fly in a transparent way to services and ship that data to a UI, whatever UI means in this context, we're basically done. Think about it. We can now change each service independently from all the others, because they have full ownership over the data they own, and that's more than enough. But let's try to dive into what's the user interface problem we're trying to solve. There are two main approaches to solve user interface related problems when it comes to distributed systems. One that is called branding. Branding basically is a fifth service in our scenario. So we have catalog, shipping, sales, warehouse, and branding. Branding owns the UI schema, as warehouse owns the schema in which the schema used to store the product inventory, and sales own the schema to store prices. Branding owns the UI. So branding is the one that dictates this. Branding is the one that says, I'm going to design a UI like this one. And in this case, this is ASP.NET Core MVC, but it can be Angular, React, whatever you want. So what branding is saying is, I'm going to show this. These are the information that I need. I need a product description. I need a product price. I need a product shipping options. I need product inventory. And all these information are coming from the dynamic view model returned from the gateway. So that at model thing, that is the default model provided by the ASP.NET Core MVC framework, is filled in by the composition gateway at runtime with information coming from different services. And branding couples them together to display them on a UI. And I intentionally use the word couples, because that's what branding does. Branding is a source of coupling. So branding is the technical authority owning the UI contract. So whenever we have a contract sharing data across services, we have a source of coupling. In this case, branding sits in front of everyone, dictating, you want to display something? Here is the contract you must respect. Get over it. So each service must implement that contract, or the part of the contract they own. In this case, shipping owns the shipping options only. And UI structured is defined as a monolith. So branding is the simplest way to implement UIs on top of distributed systems because they are monolithic. They're just a source of coupling sitting in front of everyone, and they solve a very simple problem. Someone is giving us data that needs to be displayed to a user in order to simplify as much as we can their buying process if we're trying to sell them something, like in this case. Is that a solution to every single use case? Not really. So most of the times branding is super handy where you have B2C kind of environments, so where you want to have fine, full control over the way data are displayed and information are displayed. And if you have small teams, or even if you have a large team that is doing only one thing, that is the UI. But not all the products and not all the companies are like this way. So on the opposite side of the spectrum, we have a thing I like to call UI composition magic, or black magic, if you will. So let's use the same sample HTML fragment coming from ASP.NET Core MVC. What we have here is that we have a very similar HTML fragment where instead of having something defined by branding, we have basically someone, in this case, who owns the product details page, catalog, for example. So catalog is saying, I'm putting the product description where I want, and then I'm saying, hey, in this space, I know that they need to put product details, product shipping options, and then inventory and price. So what I'm simply doing is delegating to someone else the act of showing data. And again, you can see these as MVC components, like in this sample, or they can be Angular 1 directives, or Angular, whatever version it is now, components, or React components. It doesn't really matter the technology stack you're using at UI level. The important thing is that each component is owned by a different service. And in this case, what Catalog is doing is simply, like if it was creating holes, or I usually call them regions, into the page, where all these regions have to be filled by a different service. In this case, the only thing that Catalog is doing is saying, hey, I know that I'm calling that region product details price, product details shipping options, and there will be someone that at runtime fills in the required information, where the required information now is not only data, but is schema and data. So if we look at this from the what's the difference between branding and UI composition at this point? UI defines only the high-level structure. So we have a very high-level structure defined by the logical owner of that specific page, in this case, Catalog, saying, I know very little of this page, so I'm putting what I know onto the page, and then everything else is filled in by someone else. It's unfortunately highly coupled with the presentation technology. So the way you do it is different depending on different UI technology stack. Branding is way less important in this case, and the more magic, the less branding. So the more you move to one side of the spectrum or to the other, so the more the pendulum swings to the left or to the right, you need less of the other part of the spectrum. And now what happens is that services, they own the entire vertical slice with UI composition. And if we go back to the picture that we saw before, we can say now that UI, the user interface gray segment, can be displayed like this, where we have each service deploys into something that we can now start calling a client shell components that are technology dependent on the technology choice on the client side, and they know how to display data coming from different services. Why should we do this? Well, one of the questions is that we need to be able to answer is, how fast do we need to react to changes coming from services? Because in the branding scenario, where branding is monolithic, if something changes into a service, the only thing we have control over is one of the handlers into the composition gateway. So what happens is that if, for example, sales wants to start using different currencies, so they need to start differentiating the concept of a price that is not, maybe, let's say, it's not euros anymore only, but it can be euros, US dollars, and all the currencies that comes to your mind. So they need to have an additional field that is the currency selected. So in order to display data, they need to change nothing, right? Because they can have multiple fields now into their own storages representing the value of the price and the currency, but when data are composed to display on the UI, in the handler, what they can do is that they're just returning a string to the UI. So what they can do is that they can join the price and the currency information to return a string like it was before. It's not euro anymore, but it's always a string. But there are changes that might affect the UI as well, in which case branding is a limiting factor. So if changes like this are not coming from branding, then the fact that branding is monolithic limits the ability of services to a certain degree to change as they want. That might be a good reason to move to full vertical ownership, saying, hey, I want to have full control over UI composition process as well and components deployed into the client shell, so to be able to adapt to that rate of change way much faster. What's the problem then? Obviously, complexity is one of the problems. The thing is that if you think about it, it becomes more and more complex to deploy components. It becomes more and more complex to test the UI. It becomes more and more complex to guarantee consistency, because now styles are split into services. JavaScript that runs in the UI is split into services. And now it's easier that something goes badly at deploy time because we are overriding each other's styles. And so the complexity increases, and there have to be good reasons to handle that complexity. The slides are already available online at the second link, and 4 demos demoing composing one single product, composing a list of products, demoing how to use branding and how to use UI composition are available at the first link. So before looking at some sort of conclusions, is it worth the effort? My answer is generally no. So complexity increases, it's already complex. And it gets even more complex as black magic kicks in. So if we want to move from composing data, what we call view model, so from view model composition to UI composition, that it means even more complexity into the system. So all this complexity has to be justified by something. And that's usually the dimension of the project, the expected life cycle of the project, dimension of the teams, the rate of evolution, all factors that are not really technical related, are much more business related. They need to be factored in before making a decision. Do we want to go down this path, or shall we stay monolithic? Because it's simpler to break a monolith later than doing the other way around. So it's better to build the monolith first and then break it apart once we have understood all the caveats of the domain we're designing, instead of building a distributed system first and then trying to fix all the distributed monoliths problems that we're causing because we have no real clue of the domain we're building. So try to avoid complexity as much as you can. Takeaways. So the most important thing I'd like you to take away from this short presentation is that boundaries are the most important part. So finding and defining service boundaries, or bounded contexts, if you prefer the domain-driven design lingo, is the most important thing to do before starting to design anything. And one interesting signal that we might have found wrong boundaries is the need of technology. So as soon as we start saying, oh, we need more technology here, we need a cache here, like in the sample that we used, that's a smell probably. So use that as a signal to hold on a second, step back, go back to the drawing board and verify why you need that additional complexity to maybe solve a problem that is not a technical problem. It's more of a business problem or over a design problem. What can lead into that direction is what I call the user mental model. The user mental model is usually used as a leading design factor. That's a very interesting way of designing softwares. We're translating the user mental model into the software. The problem is that when it comes to distributed systems, the mental model can easily influence the design in a bad way. Because the problem is that users, they tend to think to data in terms of data presentation. They talk about products. And what we do as engineers is that as soon as someone says product, we picture out in our mind public class product, description, public string description that gets set. And now we created the design, the service design, the service boundaries following the user mental model and not the way data are really distributed into the system. So, and finally, you can use view model composition to present data. So there's no need for complex projections and read models, because if we have split data correctly into services, the only thing we need to do is to extract this data at runtime and show them. We can do that on the fly. And if we really need to cache for performance reasons, we can do that at each service level. We don't need to do that into a sort of land of nowhere kind of cache. As said before, my name is Mauro Servienti. I'm a solution architect for particular software, and I was very happy to present to you today, and thank you very much.
Thank you very much, Mauro. It's a pretty complex content. It's always a huge challenge to work with microservices. It requires a lot of maturity. I have seen a movement in many companies moving from first they moved from a monolithic to microservice, and after some problems they are going back to monolith because they realized they didn't have enough maturity to working on. Thank you so much for this presentation. It was a really clarify. It's not easy to talk about a deep content like that in just 1 hour. I hope your participation in the future for more talks like that. Thank you so much.
Thank you very much. Let me add a couple of things to what you just said. It's one of the interesting thing when you, if you look at the history of large companies, like for example, eBay has a nice paper describing their the changes they applied to their architecture over time. And before going to a distributed system like they are now, they went through, if I recall correctly, I don't remember if it was 4 or 5 different monolithic versions. So the first 5 releases of eBay were huge, ugly, horrible monoliths. And they used those to have a deeper understanding of the domain they were in. So only once they were pretty sure about the domain, they decided to say, okay, we're now ready to do the next step. That is, the domain is stable. We know everything. We're confident with that. We can split that into services. Because once you distributed the system, changing that is a much, much harder problem. That's why going distributed as the first release is probably the worst error you can do. It's very easy to fail at that point.
I usually say that the first argument or reason for a company to move usually to a distributed system, it's like because Netflix, because Uber, because another big company is doing, or let's do that, because if that companies are using that, it's good and we should follow the same practice. But my answer is always like that, like, do you have the same team, the same people, the same resources as these companies have? So
correct. Correct. It's I answer something like that when people ask me, can we have a Google-like search? I'm telling them, yeah, give me the Google budget and you'll have the Google-like search. Right? It's essentially the same thing. They see these companies that they're doing heavy engineering related things, and they don't realize, well, but I don't have all these problems.
Yes.
That's the, and let me answer. Let me add a comment. That there's a comment in the live chat from Nicholas, and yes. So basically, each view model can be created exactly to satisfy client needs. So regardless of the fact that you're going down the branding path or the UI composition path, that doesn't really matter. So if we think about data only, services, they just own processes and data. They don't care about the fact that data are showed somewhere. So they just own these two things. And there's a UI team that might be inside the same service or outside, like in the branding case, saying, hey, I need to display your data on this page in this way. Can you give me a view model? Yes, here is a composition handler that does exactly what you need. And that builds a view model exactly for that specific purpose. So basically, for every use case that you have in the system, you'll end up having one or more composition handler coming from different services to satisfy that specific use case. So you end up with many tiny components doing one single thing. That's the single responsibility principle to its extreme, to some extent.
Yes. Perfect. Thank you so much, Mauro.
Thank you.
See you in the next events for sure. I hope we can meet each other around European events. Probably next year, not this year.
Yes. Yes. So. Yes. So. Unfortunately.
Thank you so much. I'm gonna.
Thank you, Mauro.
Thank you.
I'm gonna share the Yvan screen. So your screen is being shared, Yvan.
Okay. Thank you, guys. So, just to introduce myself again, my name is Yvan Polevich. I'm more known from the Clean Architecture Manga project, and this talk is an introduction to the clean architecture style, and I'm gonna show you how is the approach by following these principles, practices, and patterns. So let me. Okay, I'm also support a YouTube channel, polevich.net, some blogging on polevich.net website, and I used to be MVP, and now I am on the Reconnect program. And to begin with, what is clean architecture style? And to talk about this subject, let me see some historical around the subject. Clean architecture is an evolution that was made from ideas from different architecture styles. So one of them was hexagon architecture, onion architecture, screening architecture, and these other architecture styles influenced mostly Robert Martin to design his proposition of what is a clean architecture application. And one of the characteristics is that a clean architecture produce systems that are independent of frameworks, testable, independent of UI, and any other external agency. So the outcome of a clean architecture application is a software that has these characteristics. But let's see a little bit about the style that most of the time is implicitly said, and style is a particular procedure, a distinctive appearance, typically determined by principles according to which something is designed. So I think when you talk about the style, there is something particular that calls our attention to it. Okay? And when we talk about clean architecture, I've seen many definitions that, oh, clean architecture is hexagonal architecture. I don't think so. I think hexagonal architecture is a concept that is part of the clean architecture style. Clean architecture style adds other concerns and hexagonal architecture, we need to understand it first, then we expand to other principles. So first of all, let me recap the hexagonal architecture style so we are on the same page. To begin with, hexagonal architecture style has this ports and adapters pattern, dependency inversion principle, and test-driven development. Interesting here is that I don't end my definition by the ports and adapters pattern and dependency inversion principle. So it is not only that. I'm adding here test-driven development as a practice that complements your hexagonal architecture style, because we are going to see how it works. And adding to this concept, clean architecture style adds object-oriented design principles, use cases as a central organizing structure, and this pluggable user interface that is sometimes hidden in the definition. So hexagonal architecture style has these patterns, ports and adapters. The implementation is guided by tests and also is decoupled from technology details. First, ports and adapters. Usually we have this representation in a hexagonal, but it has some historical, but also when you see the components being drawn here, you see that the image looks good. But ports and adapters, what are ports? Ports are the interface in between the application layer, the business implementation, and the external world. If you are going to a database, to a cloud service, or the user interface, the interface will provide, will describe this capability. And what are examples of ports? So here I have the POST use case, the POST output port. These are interfaces that are called. So for instance, the deposit use case has a single method execute. And I think most common is the account repository here. It's the repository pattern that is responsible for the state management of the account aggregate. So these interfaces are defined inside the application boundary. So it's known by the application and is defined in the best way for the application. Later on, the adapters are the components that implements the specific details to consume the external resource. It can be the database, the cloud service, and even the UI is an adapter for the application. But interesting here that you see that each adapter in yellow they have this in-memory SQL, in-memory messaging, and then the specific cloud messaging, because we are going to see that the intent of the hexagonal architecture style is to run, to develop it, and to test the application in isolation. So the application needs to actually run independent of external agencies. So I'm adding here the fake in-memory persistence, the fake in-memory messaging, and the tests, because the same way the tests provide a fake user, the in-memory persistence provides an illusion of a database. And the in-memory messaging provides an illusion of a physical messaging mechanism, or maybe a cloud service. So later on, how looks like an adapter. The adapter is usually a set of classes. For instance, the persistence adapter needs to have the entities, repositories, context, because this is a entity framework implementation of the persistence mechanism. And usually, the classes that live in the adapter, they are very specific to the framework, to the technology, so they are tight coupled to the technology that they are providing capabilities. Very concrete classes, like this is what it is, so it ends there. When you put everything together, this is the representation that I see that adds more information to understand the hexagonal architecture. So ports and adapters, we have this each component that provides a loop back that instead of going to the database, it says, okay, instead of going to the database, I almost go there, but I return, because it's an in-memory messaging, in-memory persistence. And what is interesting here, when you have this setup with components that provide the concrete and real implementation and its fakes, you can define at execution time that, look, the application is going to run not against the real database, not against the messaging mechanism, but using the fakes. And it is very useful because I think most critics about this is, oh, I'm not going to change my SQL database to Redis database at any time. This never happened. But let me tell you, I'm not designing my, actually, it's a consequence that later I can change my persistence, I can change my messaging. It's a consequence that I always get those benefits. But when I start software development in the iteration 0, I want to deliver software to production, which means that when I start the development, I don't have the full definition of the database schema or the messaging or the user interface. Usually, I have a fragment or those definitions because I'm working side by side with a partner, and they gave me an idea of how this partner web service works. So what I do, I can write my business implementation against a fake implementation that I defined as my mocked service. So I always move my database persistence, but not from SQL to Oracle. I'm always start my development, and then on the iteration 0, I put software in production that can be used by the user in some way or another to understand better the problem. But later on, when I have more information, I implement the concrete and physical service that goes to the cloud or to the partner. So, and interesting thing about software in hexagonal or clean architecture is the bringing up use cases to the definition of the software. Because nowadays, I think we always start software by this templating structure, following the famous project templates, and all the projects look the same. But even though one is an e-commerce website and another is a private website that you had. So different business having exactly the same architecture, the same design. But talking about hexagonal and clean architecture, the use cases are explicit in the most important part of your software. And use cases are simple algorithms that receive the input data, execute the algorithm, and generate some output data. And when you see this implemented like in code, you can see what are the primary actors, the ones that are using the use case, calling it, and what are the effects, what are the secondary actors, the systems that are affected by the use case. And yeah, so they are also delivery independent. Use case do not have a user interface definition. But let's take a look what I'm talking about. So here, it's a screenshot from the Clean Architecture Manga project. Has this, in the application layer, has this folder structure where the use cases are more put on the root of the application layer as a priority, as a first class structure. And the execute algorithm as a simple method that receives an input, orchestrate different calls in the internal services, and at some point gives affects another system, in that case by calling the build output, or maybe the write error or the not found operation. So, and so input and output messages are messages. They just carry the state that enters the application and the state that is written by the application to the output. So it is one characteristic of this, in this case, is that input and output messages are highly consistent, because when instantiating an input message, you execute these validations and constraints, and the output is highly consistent because it was created by the application. So highly consistent messages. On the other hand, the deposit use case, request and response, are highly inconsistent, because these are the messages that the user interface or maybe other systems are generating, and they don't have the constraints of our domain. So, and there is one characteristic here. Those messages, they are very specific to the adapter that you are implementing. So in case of a web API, you should use all the benefits of the frameworks that give you way to serialize, deserialize, to describe the API with Swagger. So you can enrich those classes with attributes, add dependencies here. We are going to understand why, but I don't want to have those frameworks, those attributes, those dependencies in the input and output messages. And let's see here. So the user interface contains the controller and request and response messages. Those are very specific, concrete, unstable because they are instantiated from the user interface. On the other hand, the use case lives inside the core of the software, and it's highly stable, general, abstract, and consistent, because to enter the core layer, every parameter, every argument should be validated. So, and I need to point out, because I'm using these terms, concrete and concrete, abstract, and lots of terms that are maybe not familiar. And when they come, where they come from? They come from the famous representation from Uncle Bob, this concentric circles. And how can we read this? This is several layers. Each layer has a different concern. The more outer the layer, the more specific, the more dependent it is, and the more inner the layer, the more abstract, the more business related it is. So one characteristic here is the dependence are in the direction of the stability. So a component should depend on a more stable component, never the opposite, I would say. The abstractness of the component, and how can I say abstractness? So a sealed class is very concrete, right? So you can't extend it anymore. But an interface is highly abstract because it can be implemented in several ways. So the language you use, they have different ways of defining abstractness and concreteness. So the concreteness is the more outer you go. The abstractness is the more inner you go. And let me show you a slice of those pie. So here we can see that in the yellow and red, things are more abstract, general, and consistent, stable because they don't depend on different components. But when you go outer the layers, it became more concrete, and also depending on the components on the inner layers. And introducing those principles, because I don't want to, actually, it is hard to define clean architecture by rules, and that is never going to work, but defining them by principles, because if you follow the principles, you are going to see that in the project that you are developing, if you follow the principles and think about them, you are going to make a decision that makes more sense. But so the principles will guide you to design your software. So for instance here, defining stability and responsibility of components. So the blue one, you can see that there is this yellow components, and the yellow components here, they are depending on the blue one. So the blue one do not depend on anything else, which means that by not depending on anything else, it is very stable, because the only change that it needs to be concerned is its own. But it's also responsible for other components, so it can't change its implementation freely, because whenever you change the implementation, the projects, the components needs to update the reference or maybe the contract. Another component, the red one, it is highly unstable, because it's a component that depends on several others. So, but it's also irresponsible, because there is no other component calling each other, calling him. So you can change the red one, do whatever you want, that it won't affect the yellow ones. And let's see it in a classic project schema. So,
Yvan, can I ask you something?
Yes.
Nicholas Fonts is asking in the chat. I think it's pretty related to this slide specifically. What's the best layer to include validations like email validation, no label, etc., application layer, domain layer? Because there's a lot of controversy in this topic, and depends on specific scenarios. But in your opinion, what's the best approach for a clean architecture perspective?
First of all, the application and the domain are only organization separation, because they live they have the same level of dependencies. Ideally, when entering the application, the fields need to be validated, because it is going to invoke the use cases. So when entering the application, you know what is the use case, and before executing the use case, you need to validate it. But the validation that you are going to do is when the object can be validated against its structure, if they are nullable or not, if they are inside the range of the field. But if it depends on, and that is the next question, if to validate a field, it needs to read a remote access resource, it actually needs to validate in the application. So you always validate in the application, but the application is the one that is calling the validation that is implemented in the domain. I think that makes things more clear, because each domain knows the rules of those fields. So it is implemented in the domain, but is called by the application. Yeah. Okay. I guess I can continue, but we can go back to it at the end. So the stability. Okay. So, and then we are going to talk about stable dependencies. So here is a classical project, and there is infrastructure, web, and application, and they depend on the domain. That is the ideal world, right? But what happens, and that is the corporative scenario that I lived in many companies, is that some engineer find this shining framework, shining library that gives you some productivity gain to write rules and validation, messaging for the domain. So okay, and then we embrace that, and you design your domain on top of the constraints of the frameworks and libraries. And by indirection, the infrastructure, web, and application become dependent on those frameworks and libraries. And frameworks and libraries, they die. And that is one problem. But they maybe change the design. They are discontinued. And in some point, you are going to see that you designed your application not on a stable component, not on a stable domain, but on an unstable domain. So the stability should increase when you point inwards the application. So if you have a component that is stable and you are depending on an more unstable component, well, you are not following the principles. So that is one of the ideas that I'm bringing here. So follow the principles, so you don't have to follow the rules. So to know the rules. And as I said before, I support this Clean Architecture Manga project, and I just want to walk through the use cases. One is the deposit use case, and talk about relevant structures, how it works. So it's like drilling down the code. So the deposit use case starts in the controller. The controller is part of the user interface, and it receives a request object. This request object needs to be converted to a valid input message, and otherwise you can't execute the use case. So this is implemented, and the interesting thing in this implementation here is that there is this mediator that knows all the use cases and will route input message to very specific use case. So when you send a message deposit input, it will invoke the deposit use case. And the next step here is that the use case is an algorithm. So in this case, it needs to see if the input is null. So it still needs to validate it. In this case, it is retrieving an existing account from the database, but the database is implemented in the infrastructure. And in this case, it's a empty framework implementation of it, and it will return. And that is another point here. It always, when you see a method, and you have two options. One, when you have a method and it has side effects. When a method has side effects, you can call another object, passing the side effects, or return an object. If you choose to return an object, it should be highly abstract. So in this case, it's iAccount, and the implementation here knows that iAccount is also an account object. And then it comes back to the use case, and then it needs to call the domain service that actually makes the deposit into that account. Which needs to create a credit transaction, execute the update method, but this update method, in this case, the repository is connected to a unit of work operation, so it do not commit to the database. So the update do not affect the external resources. But then the unit of work can be called with the save method that actually persists it into the database. Next is the side effects. I could return a message, right? I could return the deposited account with the transaction. But if you follow the design of the manga, whenever a use case has a side effect, I invoke the presenters because I defined for the use cases alternative outputs. So it can be an error, not found, or maybe the standard output. And I'm defining this as a contract that the user interface needs to implement and say, user interface, I need to implement an error method for the deposit, not found method for the deposit, a standard output method for the deposit. And whenever it is a web API or maybe a file system, is the presenter that knows the specifics to generate this user interface. So in this case, the presenter is called by the use case, and it can generate the not found method with a not found object result, the standard with the object result view model, or maybe a bad request object result. So at that line, the presenter was initialized because it was invoked by the use case, and you can just ask presenter, what is the view model? And the view model can be any of those possible results. And I think what lacks most on clean architecture and hexagonal architecture implementations are good testing strategies. And I'm gonna introduce a few that are inspired by Martin Fowler and by learning from the contributors of the manga project. So the biggest challenge is that an application is made of this web of objects that reference each other, they call each other, and should I test all of them? What is my approach? Should I call the first object that is in the main of the application and then see if everything works as expected, even though there are in the execution have many possibilities? So I don't think so. I think testing should target categories of objects and the neighborhood of those objects that they are targeting. You should know what to expect from them. So whenever you have this web of objects, you should, and you want to test them, actually, you shouldn't think like that. You should think about the test and design the target object, and those neighborhood objects, you expect some behavior from them. So, for instance, suppose that you have to write a deposit use case. The initial idea is to start with a test that you can, it's a unit test, that you can call the use case. And you are going to see that in some point, you need this collaboration from the neighborhood of objects. And what you do is to expect a constant behavior from them. And this is what I call, not, I shouldn't say what I call, but what is called by the industry as mocked objects or fake objects. I see as a proliferation of MLQ framework writing these tests that are highly dependent on frameworks. And besides the dependence on frameworks, it's hardly to use a mocked object from the user interface. And let me show you something here. Whenever I'm creating an object, in this case, the deposit use case, instead of mocking the account repository and customer repository, which is a common challenge, I write a fake object. And this fake object can be called by the tests. And also, if I want to run the application, I can say user interface, instead of using the concrete implementations, use the fake ones. And later on, I'm gonna write tests against the concrete customer repositories and account repositories. And this is called integration tests. And an integration test do not mean that you have to execute all the business logic, call all those components, internal components and orchestration, and at the end, invoke an external resource, and then from the response, call a secondary resource. No. The tests, from the integration test perspective, should test the adapters in isolation, each of them. And just a simple overview, because we have, I would say that we have these two categories, the tests that are in process and the tests that are out of process. In process, they can run within the application's memory. They are very fast. They are easy to design a variety of cases. And the usual targets are use case domain objects, while the output out of process tests, they reads I/O, so they access the secondary memory. They are slow to execute in a magnitude, in an ordered magnitude much higher. They usually require this extensive setup, and the usual targets are the repositories, like going to the database, and also the services that can access anything. And this is highly inspired by Martin Fowler about this testing microservices paper, but it applies to many projects that follow those patterns of separation of concerns and needs to access remote resources. Because usually an application, a software, they have these different patterns, and let's talk about them here. So a usual software skeleton, unit tests, and calling by unit tests, those tests that runs in the in-memory boundary of the application. So you shouldn't call a unit test a method that access a database or any other external resource. These are integration tests. So unit tests, they if they need to access a remote resources, they need to access the mocked or the fake ones. In this case, the fake web services, the fake repository are needed to execute the use cases. And integration tests doesn't mean that the integration test needs to execute the controllers, the use cases, call repositories, and call services, and then you assert it. This is not the case. An integration test is, let me invoke the repository, all those methods that are needed for the repository, and those methods that are needed for accessing external resource. And component tests are to say that can the application be loaded correctly if I know what is the expected behavior from my remote resources? So you can test the component test in isolation of any other service. And then we get to the test pyramid. The unit tests are in the base because it is easier to create a variety of unit tests. They are quite cheap to implement them because you just need the in-memory resources. The component test is also in memory, but they need to know a large piece of the software because they need to set up them. And the integration tests is another category of objects of tests that are quite expensive to execute. So you only need to implement those methods, the tests that access the database schema and the resources. There are other tests categories that you can have, but ideally you have the cheap ones at the base and the more expensive ones at the top as a lower amount of them. Okay, and to wrap up the clean architecture. Clean architecture is about use case, a central organizing structure. So you design tests, and those tests needs use case implementations, and those use cases depends on external resources, and these external resources are interfaces. So the implementation is always guided by tests. The user interface and persistence, they are designed to fulfill the core needs. And whenever someone say, oh, I'm never going to change the database, I would say that I am delivering software on the iteration 0, and the iteration 0, it runs in production, and I can call the customer and say, test it, and at least the business logic can be validated, even though the database is not well designed. And many thanks to those contributors to the Clean Architecture Manga. If you are a committer or if asking questions, issues, opening issues, all of them, many thanks to you guys because it's a lot of help. And also Robert Martin, because I think he created lots of resources from the Clean Code series, and his books and are fantastic inspiration for me to implement the Clean Architecture Manga. And next questions, and I see that we have another question about database validation. Oh. Okay, how can we check an object that depends on external resources? And that is why you need to validate in the application layer. Actually, from the previous question, I said that it's the fields need to be implemented, validating the application layer. But even before entering the application, it needs to be validated because the input message is highly consistent, but the implementation of it is part of the domain. And if you need to validate something that depends on external resources, you call it in the beginning of your algorithm. Because when you define a recipe, this is your use case. And if in the beginning of your use case, you need to validate these fields like a duplicated registry, it is defined on your algorithm, and you can implement it there.
So the separation of software architecture, it's quite clear in the majority of cases, but I have seen some companies are not so good strategy to separate the unit tests, the integration tests. How usually you separate mainly your integration tests? Like if you have, for instance, 50 classes in specific business logic, are going to separate the integration tests like in folders, one for each class? How do you manage that usually?
Yes, let me see. I think the purpose of the tests, they also guide you how the application is going to grow. And usually, we have this use case as a entry point of the application. So this is a major organizing for the tests. So I think each test, each use case, you need a test for them. And the collaboration objects, like if you need to validate the name, the phone number, these are tested by consequence of running the use cases, the test cases. Because and there is a code smell on tests, and the code smell is if you have for each class in your software a test class, it means that you are not testing the objects in collaboration. You are testing the object in separation of each other. So you need to set a level of collaboration between objects, and each collaboration is a test class. But when you talk about integration tests, I think you need to have an integration test for each external method, external operation that is needed for the application to run. So, and end-to-end tests or maybe component tests, I think you have much less of them.
Yes, because a single component test like covers a lot of methods and code, and usually I make a decision to prefer to write integration tests instead the unit test, because usually the integration, if I don't have time, a single integration test probably will run like many methods, like a compound, a lot of objects and interactions, and a single test will attach a lot of things if I don't have enough time or resources in the project to do that. But there's a lot of discussions regarding to that, because the unit test is the cheapest one.
Yes, the thing is, if you write the unit tests on the beginning of the project, it will guide you to a better design of the software. And instead of finding bugs with integration tests, you prevent them of being added to the code base. So I usually prioritize writing unit tests, but not after, trying to bring them to help the design of the software at the beginning.
Considering your experience in international projects, open source projects, do you think the developers nowadays are more aware of the importance of tests than before, or do you think the companies in general and the projects are skipping this important part of the projects?
Well, I've seen a lot of growth into hiring developers that had this practice. I think the bar is growing, it's getting higher. So I can't say that is a common practice, but it's definitely something that if you are familiar with that, it will help you a lot into any hiring project, because if you know that, you became a multiplier in the team and you raise the bar. And that is what I've been living into hiring developers. And whenever I join a hiring, I'm applying for a job. If I show this, is definitely something that attracts employers to say, well, this guy will raise the bar in the team, and the quality will be from the development perspective, not after the development.
So thank you so much, Yvan, for the participation. Feel free to join in the next events.
Definitely.
This video will be available on the CaquiCoders YouTube channel. I know for who is not Brazilian, will find Word, the other videos in the YouTube channel in Portuguese, but no worries. We start to have more content in English as well. And as far as we have enough time, we will use closed captions in English in the other videos as well. Thank you so much, everyone. See you in the next event.
Okay, bye.
Bye-bye.